And we want to expand out our discussion of cells to some more applications using what's called the Nernst equation. So far, when we've been talking about cells, we're looking at everything under standard conditions. So our electrolyte concentrations are all going to be 1 molar. That's this idea of standardization. We have those tabulated reduction potentials. So, you can do things like predict what would oxidize, what reduces, your anode, cathode, that kind of stuff. The thing is, that's pretty rare in real life. One, it's hard to set up. You'd have to get everything right locked at 1 molar for your concentrations. And another important thing is that as your cell happens, as electrons are transferred, your reactant concentrations are going to decrease and your product concentration is going to increase. That's just the nature of doing chemistry. So standard conditions are hard to create, and if they ever are created, it's guaranteed to be temporary. So we develop or use what's called the Nernst equation that lets us understand or predict the potential for a generic cell, which we're just going to call E cell. So that just means the potential of a cell. You'll note it's missing the little knot that implies standardization. So this would just be for any given cell of whatever concentrations, whatever you got, what is the potential? And you can see it's based off the standard cell potential. So we can still get that. That still gives us information that we can get from tables, our kind of piece of reference information. And then we basically plug that in and basically modify it. And we can see it's modified based off with our first is RT over NF. So these are variables that we've seen previously. R is the ideal gas constant, T, my temperature in Kelvin, N, the number of electrons transferred in the balance equation, and F is Faraday's constant. So we've seen N and F previously when we looked at delta G for cells, and then also R and T we've seen previously. And then another thing making a comeback is our Q reaction quotient. So this would be the reaction quotient that we talked about when predicting how things transfer to equilibrium. So coming up here, this is kind of, basically this description of how it was looking at how do reactions kind of evolve as they change, concentrations and stuff like that. Same idea. So the overall Nernst equation looks like this. This is the most generic form. I will usually start with this form, but you can substitute some constants. So for example, R is the gas constant, F is Faraday's constant. So those are just given numbers. You always know what those things are. You can plug them in. They're always going to be the same. It is also very frequent that you do these sorts of use cells at room temperature. So your temperature would be 298 K. So sometimes people plug that in, and you'll see forms of the Nernst equation that look like this. So this is a simplified form of the equation. This right here is always actually generally true. This bottom one's only true at room temperature, which is very, 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 very common. But I like to keep things as generic as possible. This is the true Nernst equation up here. Whatever you want to use is going to work. You just do want to be mindful if you're not at room temperature, this one ain't going to apply. So you do want to be mindful of that. This one is always true. The second one is always true. You're just defining what those constants are. So when we want to get some practice using the Nernst equation, it's going to be worthwhile to review reaction quotients, Q. So let's see, what would the reaction quotient be for the following electrochemical cell at standard conditions? I got a cell notation description. Let's see what this looks like.
So we want the reaction quotient for this cell. And we know our reaction quotient, that is going to be our Q that we're looking for. And so this is going to be related to, we're talking about characterizing reaction mixtures at equilibrium kind of stuff. And so in order to come up with this, what we need is the chemical equation. So we have our cell potential, or kind of our cell notation written out for overall what all the components of the cell are. What we also want to do is kind of add in some explicit information, or kind of explicitly come up with what the chemical reaction is. So we can take our information. We know that this is one of our half cells, Zn solid becoming Zn2 plus aqueous. And we know we're always going to start with our anode, so that should be the oxidation. And when we go to balance it, it makes sense. Electrons are a product. So then our cathode is copper 2 plus becoming copper solid. This is the cathode. It should be reduction. When we go to balance, electrons show up on the reactant side of the equation. So what we want to do, so these are our half reactions. We want the overall chemical reaction, so we need to combine them. Everything's been swapped. We would potentially need to worry about balancing our electrons, but they're both at 2 here. So we can take them, add them together, zinc solid, Zn2 plus, aqueous, plus the 2 electrons. We add to that 2 electrons plus the copper, 2 plus aqueous, copper solid. The electrons are going to cancel out. And so it's, zinc reactant, copper 2 plus reactant, zinc 2 plus product, and then copper product. So, when we're using the cell notation, it's reactant product. So that works out. We now want to come up with our Q expression. We know it's going to be, the idea is a ratio, just like our equilibrium constant, of products over reactants. We don't worry about the solids because they're solid. We only care about the aqueous, so the concentration of the zinc 2 plus and the concentration of the copper 2 plus. So that's going to be my generic equation or expression for the reaction quotient. We can also get the explicit value for it because we have our concentrations. We're under standard conditions, so the concentrations of all of my dissolved things are 1. So we can plug those values in. 1.0 divided by 1.0, we get 1.0. So this is under standard conditions. Q is equal to 1. You'll note standard conditions, when we defined it, was only based around concentrations of electrolytes. The amount of electrode or the size of the electrode, we didn't care about that because it doesn't show up in this reaction quotient. It doesn't show up in the equilibrium constant. All that matters is that basically you have enough solid. The actual kind of position of equilibrium, how close you are if you're at equilibrium, is determined by concentrations of electrolytes. So standard conditions specifies that concentration as being 1 molar. And in general, whenever we have a cell at standard conditions, the value for Q is going to be 1 because all the concentrations are always going to be 1 molar.
So for any cell at standard conditions, because all of your concentrations are 1 and Q is a function of those concentrations, it's always going to have a value of 1. And so basically you're always going to be taking the logarithm of 1 right here. And so that's always 0, meaning that as we would expect, if it's standard conditions, the potential of that cell is equal to the standard cell potential that we would predict. So we're going to put some context on this Nernst stuff. So when we have a cell and has a positive potential, that means the reaction is going to happen, right? Positive potential means electrons flow from anode to cathode out of your oxidation into your reduction. And underlying all that is chemistry is happening. And if the chemistry is happening, that means your reaction is not at equilibrium, right? But you're going to be reaching equilibrium. So your reactants are turning into products. It's similar to, this equilibrium kind of distribution, or kind of changing to reach equilibrium. Products are formed, reactants are consumed. So in standard conditions, your Q is equal to 1, which means you're not at equilibrium, and that your equilibrium constant is going to be higher. You're going to be approaching equilibrium by going to products. So one of the things that we can start to take from this kind of conceptualization of the Nernst equation view of cells is that when the standard cell potential is positive, that means your equilibrium constant is greater than 1. So this implies that the reaction, there's this transfer of electrons, the redox reaction happens, and this implies that products are going to be forming, i.e. the reaction happens. So there's kind of this cell description that we can look at. There's also this reaction equilibrium description which we can look at, which we'll kind of return to through the course of this discussion of the Nernst equation. And so when we have a cell, we have, say, our cell in notation, we can come up with the reaction. And when the cell kind of discharges, when electrons are flowing, what that would mean is the reaction occurs, and more importantly, this reactant ion would decrease in value, in concentration, and this product ion would increase in value, right? So we would see these sorts of changes in concentrations as we go along, and importantly, our reaction quotient is going to increase as the cell kind of proceeds. So the conditions of our reaction will change. And the whole idea of the Nernst equation is to reflect how these changes of reactant and product relative amounts affects the cell potential that we observe. And we can make quantitative predictions about that. Okay, one more video left in this set. We'll finish up Nernst equation. We'll look at kind of an actual example of a cell. See you there.